Welcome back, Lesson 8, Radioactivity, Year 11. Now, Lesson 8 really is looking at some of the learning objectives that we've covered in previous lessons, namely uses of radioactivity. I know this looks a little bit messy. We're doing pages 50 to 60 in your booklets, so it's 50 to 60. And I'm just going to zoom in on different parts of what it is we're going to be learning today. So, firstly looking at different uses of radioactive materials relating to their properties such as half-life and so on, and to select a suitable isotope. Now, before we go any further, I just want to draw your attention to that table on page 50, copied over here, and it's got the characteristics of alpha, beta, gamma radiation and the different ionizing powers, half-lives and so on, with some examples underneath. So these are examples of alpha. I've written in plutonium-238 with a half-life of 87.7 years. Can you do that as well, please? Because you're going to be needing that in a moment. Quick recap before we go any further. Just remember the different penetrating powers of alpha, beta and gamma. Alpha can't go in through skin. That's why outside the body it's harmless. Beta can go through skin, but it can't go through either 5 millimeters of aluminium or 3 millimeters of lead. Gamma can go through both, and you need a few centimeters of lead or a meter of concrete to absorb it. So, radioactive materials are used in a wide variety of different situations. To fully understand each, we need to re-examine the properties of the different forms of radioactive decay, which is where that table there is going to come in handy. Bear that in mind, please. Zoom in, zoom out. Here we go. So the first application we're looking at is this thermoelectric generator. Generators generate electricity, and different to your normal generator where you'd have moving parts, you'd have magnets and a coil of wire. In this case, nothing moves. What you've got instead is a radioisotope, in this case plutonium-238, and it has particular characteristic or properties that suit the job. So the problems you'd have with space probes, because these thermal generators are using space probes, is they need to be continually maintained and serviced. They're incapable of generating solar energy efficiently, need to remain operating without human aid for long durations of time, and minimal human interaction. So, what properties the element must have? Needs to produce high energy radiation, produce heat, and have a long half-life. Question 1. Which element from the table would you use for an RTG? There's a big giveaway. It tells you here it's plutonium-238. But more importantly, why? Explain your answer. Well, I'll give you the verbal answer and you can write it down. Plutonium-238 because it produces heat, and also it has a long half-life of 87.7 years. That's your answer to question 1. Question 2. Why do you think that RTGs are only used as the power supply on unmanned devices? Well, on unmanned devices, you need something with low maintenance, and therefore you need something with a high half-life or long half-life. Plutonium ticks both those boxes, so it's ideal for this application. You wouldn't use RTGs on other manned devices, possibly because you could have a cheaper alternative that wasn't an RTG. And also, the RTG, you've always got that potential hazard of the radioactive plutonium falling into the wrong hands or not being disposed of correctly. Next page, page 52, radio imaging. Radio imaging, sometimes we use the word tracer, is able to look inside your body to find if possibly there's a snapped ligament, if internal organ isn't working properly, and it works by you get injected with a radioactive substance, often something like technetium, which is a gamma emitter, and because gamma can, I'm not very good at drawing, so this is my drawing of a person. If gamma is injected inside the body, I'll try and show it using that red circle. Then gamma can penetrate to outside the body. Alpha or beta wouldn't be able to do that. So you get a detector, like a Geiger-Müller tube, remember? And then you can measure how much radiation is being emitted from different parts of the body. Or more sophisticated image would be something like that. I'd like you now to read that paragraph, and so pause. When you've read it, press play. Now you've read that paragraph, let's look at this example here. What I've done, I've highlighted the right and left kidneys in green and yellow, and you can see that the Geiger-Müller tubes are being used to measure the amount of radiation outside the body that's coming out of both kidneys. And you can see that the right kidney, if you look again at the left and the right kidney and look at the graphs, it shows that in the right kidney, after injection, the activity rate goes up after 5 minutes, and then after 10 minutes, the kidney starts flushing that radioactive substance out of the kidney into the bladder. Whereas with the left kidney, unfortunately, it's not working properly. It's not flushing the radioactive substance out. So, sorry, should have used a yellow colour just to show the difference. So you can see it goes up as it does the right kidney, but the activity doesn't go down. That tells us the left kidney is not working properly. So the tracer is injected in the bloodstream. A normal unblocked kidney will remove the tracer and send it to the bladder. Explain the conclusion a doctor could reach about the condition of both kidneys in this patient. I've given you an explanation. You write yours down underneath, please, and refer to the right and left kidney and the right and the two separate graphs and the activity of both with time. Turn on to page 50. So when you've done that, press pause first of all, I meant to say, and when you've written down your answer, then turn on to page 53. Bit more information on what radioactive tracers can do. They can detect prompt digestive system with the heart, bone cancers, problems with kidneys, thyroid glands, and a whole host of other medical conditions. Which element would be suitable for use as a tracer? So what do we want from the tracer? Well, we want a half-life. Well, more importantly than that, of course, if you go back to my very poor drawing, you need something that can penetrate from inside the body to outside the body. Now, alpha couldn't do it, beta couldn't do it, but gamma could. So you definitely need a gamma emitter. But also, you don't want a substance that's going to be in your bloodstream for longer than is required. If you think about it, you go to the hospital, you get injected, you get scanned, and you look to see what the activity rate is outside the body. So you need something, you need gamma, and a half-life of a few hours. Half-life. Something of a few hours. Let's see which radioisotope fits the bill. We go back to the table. Find gamma. Gamma is on the far right hand side. And we go to the bottom of that column. And we're looking for a gamma emitter with a short half-life. When I say short, we don't want something that's going to be in your bloodstream for longer than needed. So all these lot will be in your bloodstream for years. Ah, now we found one that'll be in your bloodstream a lot shorter. Technetium, 6 hours. So that's a very common radioisotope to be used there. Oh, by the way, I just screenshot this in for more information about plutonium. You can always pause over that and get more information about plutonium if you'd like to. Okay, so lost where we are now. Here we go. Question 4. Which element would be suitable? Okay, I've gone through the answer with you. You can write your answer down now, please. So press pause and write your answer now. When you complete it, press play. Now you've completed question 4. I'd like you please to read through a different use of radioactivity and different medical use called radiotherapy. Now radiotherapy is something we did look at the start of the half-life topic, but anyway, I'm going to stop talking. I want you now to read that paragraph from top to bottom. So press pause, play. When you've read, press play again. Okay, now that you've read that, what you should have found out is that on this occasion, the radioisotope is used almost to zap or kill off cancerous cells. And we saw right at the start of this topic how horses can be treated through radiotherapy to get rid of these sarcoids off their bodies. And if we go back to the start of this topic on half-life, slowly, there's a picture of a horse, a before and after picture. Here we go, look. Before, it had this tumour around its eye. Wrong pen. Around its eye, let me get a red pen just here. And by using these, they look like needles. And these needles are made from iridium wire. They've been inserted into the tumour and over time have killed off the tumour. And you can see now that the horse has fully recovered. A little bit of scarring on the eye, but a successful treatment. So remember, radioactivity can be used for lots of useful purposes, not just treating humans, but in that case treating animals as well. If we go back now to where we were, radiotherapy, here we go, and you've read that page, and then you can see this is external beam radiotherapy device. What I'd like you to do now is just complete this diagram on page 54, and to do it by first of all showing the key. This is representing the gamma emitter. So this is what's going to produce the radiotherapy, and it's going to kill off the cancerous cells. So these big orange circles are representing cancerous cells. So I'd like you then just to show how the gamma rays can penetrate through these cells and then can kill off these different cancerous cells. Just think of that horse, the horse's eye, how those cells in the tumour were killed off by the gamma emitter. Okay, I think that's most of them zapped. It's a little bit like Space Invaders, isn't it? Or perhaps that's a reference not for the younger generation. You just basically is zapping all these cells. Okay, so pause, complete that. When you complete it, press play. Question 5. Explain what safety precautions a radiotherapy nurse would take if treating a patient using external beam therapy. There's one, there's the other. Remember that badge? We learnt about it earlier in the topic. It measures the level of radioactivity that a person is exposed to. So measures radioactive exposure. I'll just write down a few keywords for you, and then you can use those to answer. And then this is a lead shield. If you remember, lead is a good absorber of radioactivity, and because radiotherapy uses gamma radiation, then you need a lead shield so it protects her internal organs. So I should be writing 3-4 sentences there to explain. Press pause, complete. When you completed, press play, and I'll turn on to page 55. 55, we have a past exam question, 6-marker, not in the traditional 6-marker sense, but split up into 3 subsections. Okay, now that you've read through that question, I'm going to just write down a few keywords to help you. Explain why the alpha source are unsuitable for both types of radiotherapy described above to be effective. Well, alpha it's ionizing and not penetrating. Now the important part about ionizing is if something's ionizing, that could cause cancer because it mutates cells. And also you want something that is penetrating because you want it either to escape out of the body if you're using internal radiotherapy. Let's just look at, there we go, I'll just highlight for internal radiotherapy. Now let me just adjust the width of that. But also, if it's external radiotherapy, it needs to be able to penetrate into the body. So, alpha is no good because it's ionizing, which makes it actually more dangerous to the body, and it's not penetrating, or can't penetrate through the body. Part 2, remember you're writing down this in your own words. Just why gamma rays used in brachytherapy are low energy compared to those using external gamma radiotherapy. Well, because the in brachytherapy, remember this is internal, the gamma is already inside the body. So you just need enough energy to kill off the cancerous cells around it without if you put too high a dose of gamma inside the body, it would actually cause more damage than it cured. So it needs to be low energy so it doesn't cause damage to other parts of the body. Explain why gamma rays, so I'm on to part 3, are used to treat cancer tumours. Well, it's very similar to the first part of the question. You use gamma because gamma is not ionizing. It's not very ionizing, and it's got high penetration, so it can escape out of the body, which is useful for the internal brachytherapy, but also can be used to through external radiotherapy. It can penetrate into the body, and alpha can't do that. So to get the 2 marks, you need to talk about is ionizing, low ionizing property, and its high penetration property. Now, very similar to traces in the body, if you think of blood vessels like pipes going through the body carrying blood, you can use the same principle in detecting for leaks in pipes. So you can see these workers here on the right hand side, what they're doing, they know there's a pipe that's running underneath the ground. I'll try and draw where the pipe might be underneath the ground. And if there's a crack, a leak in the pipe, what you might have, you'd have the water flowing through this pipe, you might have a build-up of water underneath the ground. So what they actually do is inject some radioactive source further up the pipe, and then using look, there's a Geiger-Müller tube, using that detector, they walk down the path and they'll be chatting away. Yeah, this looks like normal background radiation. That's about 17 counts per minute. That's a usual value we'd get for around here. And then be walking further down. Oh, hold on a second. What's going on here? Look, my detector now has jumped up to 200 counts per minute. I'm making these numbers up. How on earth can that be? And then he'd hold the detector closer to the ground. Oh, something strange is happening here. There must be a leak in the pipe. Now what they can do then, they would just dig up this bit of ground that I've just made a real mess on. Dig up that ground, find the leak, and they would just then need to replace a small section of the pipe, and it saves digging up the whole of that path. So, write out the 3 sentences in the correct order to explain how a leak may be detected. You're going to use these 3 sentences here, and you've got 3 numbers 1, 2 and 3 to help you. And number 1, that's where the radioactive source is injected, 2 is where you got the leak, and 3 is the detector. So all you got to do is number these 3 sentences 1, 2 and 3. I'm not going to tell you, you can work it out. So press pause and do so, please. Just number them 1, 2 and 3. When you've done that, turn on to page 56. Well, question 8 and 9 you can answer. First of all, for question 8, which isotopes would you use for leak detection? Well, it's got to be able to penetrate through the ground, so it needs to be gamma. And also, you want something with a short half-life, because you don't want that ground being radioactive again longer than needed. You only need it perhaps for a few hours. So again, something like technetium would be a good radioisotope to use. Now, moving on from, so press pause, complete question 8 to 9, just here please. Okay, if you've completed, press play, and we'll now look at an industrial use of radioactivity thickness control. Press pause and read that paragraph. Okay, haven't read that paragraph. A couple of things you need to pick up on. Firstly, that beta radiation is used because the way the system works is that you get a sheet of paper. I'm trying to represent that with that green line. You've got a beta source one side and a detector the other side of the paper. Now, the thicker the paper, the less beta is going to penetrate through. I'm going to show that a slightly different way.
The reason they use a beta source is able to penetrate through the paper or aluminium, depending on what's being used, and able to be detected on the other side. Alpha particles would not get through and gamma would go through regardless of the thickness. So how it works is there is a beta particle source here which is able to pass through the material sheet. Now this detector will detect the amount of beta particles that pass through. Now depending on that amount we'll adjust the rollers on this side. Now what the rollers do is they can adjust thinner or they can move apart to make it.
Okay, so these rollers, as he's saying, they can move up or closer to each other. If they're closer to each other, the paper's thinner. More beta gets through. The detector detects it. And if it gets too thin, you get too much beta going through and the rollers move apart. Clever system. Alpha is no good because alpha won't get through any paper or aluminium, whatever it is you're measuring the thickness of and controlling the thickness of. Gamma will just go straight through. Therefore, beta is perfect because the thicker, the amount of beta that makes its way through or penetrates through is proportional to the thickness, or I should say inversely proportional to the thickness of the paper or the aluminium. In other words, the thicker the paper, the less beta gets through. Gamma would just go straight through. It wouldn't be affected by thickness.
Thicker. Now that all depends on the reading that they get from the amount of beta particles that come through. The risks for...
Okay, you get the point. So that diagram's a lot better than my scribble there. So it works for foil, paper, and some other materials. Turn on to page 57. We're now going to put that newly acquired knowledge into action. So I'd like you now to answer questions 10, 11 and 12. This is a self-assess activity. So what you need to do is pause the video when you've completed, press play. So pause the video now please. Okay, before we go over it then, just make sure you understand what's happening. One radioactive source emits beta radiation. less penetrating, because you want it to be affected by the thickness of the material. You've got a Geiger Muller tube that goes right the way across here, detects the thicknesses at different parts or at different widths of the sheet. And the Geiger counter measures radiation. Use a Geiger counter. The thicker the sheet, the lower the reading, and if it's fed back to the thickness controller. So, question 10. Why are beta sources used for thickness control applications? I mentioned earlier, because the amount of beta that penetrates the material is affected by the thickness of the material. Question 11. So you mark yours in relation to those answers. State with a reason which radioisotope you would choose for use in a thickness control machine. How would you arrange the source under the sheet? So 2 parts there. Well, first of all, the radioisotope needs to be beta, and you'd want a long half-life. You don't want to be changing the source every day or so. So you should have looked back up at the table and found a beta source with a long half-life. Here's a table. Here's beta. If we go down that column, so you choose something here with a long half-life. Obviously, you'd want to know more about how much they cost and so on, how easily they're sourced, but perhaps something like strontium with a half-life of 28.5 years would be an appropriate choice. But you could choose any really of those there. You wouldn't use iodine, because iodine would have a very short half-life and you'd have to keep changing the source all the time. The second part of the question was asking, how would you arrange this source under the sheet? Well, you would make sure that the source was directly underneath the Geiger Muller tube. So there's the source, and you make sure directly underneath the Geiger Muller tube. Question 12. Why is it important that the Geiger tube is long enough to stretch across the whole sheet? Well, the answer, it needs to be long enough to stretch across the whole sheet to check the thickness of the whole width of the sheet. You wouldn't want one side of the sheet thicker than the other. Make sure then, please, you've answered, and if you've got them right, tick with a red pen. If it needs correcting or improving, again, do so with a red pen. A couple of other applications here of radioactivity: checking metal welds, and the penetrating power of gamma is used in this application. I'll just ask you now then, please, if you can read through this section here yourselves. And when you've done that, press play. Okay, and then finally, before we do some more, look at some more questions. Radioactivity can be used to sterilize, that means kill off harmful bacteria from food, scalpels, surgical equipment, and other products. Again, press pause, read that paragraph, and when you get to the bottom, press play again. Okay, so what I want you to do now is to answer these 4 questions underneath. And when you've answered all 4, press play. So pause, answer the questions. When you finish 16, press play. Okay, so question 13. Read the passage above. Bullet point 3 advantages of this usage of radioactivity. I've just gone ahead and highlighted 3 that you could put as bullet points. 1, harmful bacteria on instruments. The second point here, no chemicals are added, so it doesn't affect the product. And also they don't need removing from the packaging. Question 14, explain which radioisotopes you could use for a machine that sterilizes medical instruments. So again, ask yourself, what are the properties? Well, it needs to be gamma. It says so above because alpha or beta just wouldn't be penetrating enough. And you'd want something with a long enough half-life. So those are the 2 properties. And again, what you need to do then is go to the table and find something that's gamma with a long half-life. Okay, here's the table. So really anything here fits that criteria, that it's gamma radiation and it's got a long half-life. Question 15. Why is it important that the sterilizer machine is surrounded by a thick lead shield? That's to protect workers and users around the machine. And question 16. Some types of food are treated with gamma rays. Strawberries, onions, potatoes and spices can all be sterilized this way. You'll notice that there's part of this question missing, so you couldn't answer that. So apologies for that. Now turn on to page 59. Smoke alarms also use radioactivity. Every house should have at least 2 smoke alarms in place. They've saved many lives. Each smoke alarm contains a tiny amount of a radioactive isotope. Now you'll see here that the source is alpha, and the way it works is that there's a detector which is reading the amount of alpha being emitted. Remember, alpha is harmless outside the body, so don't worry if you're passing a smoke alarm, you aren't going to be affected by it. The only way people get affected by alpha if it's inside the body, if it's breathed in or gets inside the body somehow, because then it can ionize the cells inside the body. So you can see there's a current that flows from positive to negative, but then when smoke is introduced, that current stops. So question 17 is asking, explain why americium-241 would be a good choice for the radioisotope in a smoke detector. Again, what we need to do is look at the properties of americium and why doesn't a smoke alarm need a lead shield around it. Again, what I'd like you to do is answer those 2. When you've done that, press pause first of all, answer questions, then press play. So you can see from the table again that americium, I made a real mess of this table, americium here, look, 241, has got a half-life of 432 years. So it's going to last a long time. And also, it's an alpha emitter. Question 17, remember, answer is it's alpha emitter with a long half-life. Question 18, why doesn't a smoke alarm need a lead shield around it? Well, I did mention earlier, it's an alpha source and does not penetrate past a few centimeters of air. So you can imagine the alpha wouldn't penetrate through the plastic and wouldn't go through the air, so it's harmless to anybody walking by. Next one, quick activity. You've got to rearrange those sentences to explain how a smoke alarm works. And there's a clue at the bottom. So again, what you need to do is rearrange them, and then I'll start you off. Look, the first one is the source emits alpha particles, H, and the last one, time to get out of the house. So what you would do, you would put H as your first one, and then Y would be your last one. So see if we can put those now in order. That'll be 1, 2, 3, 4, 5, 6, 7, 7, 1, 2, 3, 4, 5, 6, 7, and that will be 7. When you've completed it, press play. Well, I didn't realise Mr. Ruddy, who creates these booklets, is a Cliff Richard fan. Again, perhaps that's a reference from years gone by. You might have heard the Cliff Richard song, "We're all going on a summer holiday," which is one of Cliff's big hits. Thanks for that, Mr. Ruddy. So we're almost there. We've almost come to the end of the booklet before we do the exam questions. Radioactive decay. Pause, read, and play. So just to finish off this topic, there's just a paragraph there make you think about the pros and cons of radioactivity. So on the one hand, highly dangerous, and on the other, lots of different uses that we looked at today and very beneficial. It can save lives. And then at the bottom it just shows what happened back in March 2011. Now, 10 years ago. So you'd have been about 5 or 6 then. You might remember that one. If you couldn't remember the Cliff Richard song, you should be able to remember this. Yeah, a nuclear power plant, unfortunately, was affected by a tsunami. And you can see the exclusion zone around that nuclear power plant. You might have also heard of the Chernobyl disaster. It's an excellent TV program. I think it was a 5-parter. It was on either last year or probably the year before. If you ever get a chance of watching that program, it was based upon true story of what happened in Ukraine, which was then part of the Soviet Union. I think it was 1986, and there's still an exclusion zone around that nuclear, well, what was a nuclear power plant now. Anyway, that is the end of this lesson. So please make sure you complete the plenary. That's on Study Zone going with it. See you next time. Bye.